How do LLMs deal with edge cases? Executive summary: LLMs excel at common tasks, but struggle with edge cases, rare, ambiguous, or adversarial inputs. Their limitations stem from uneven training data and reliance on probabilistic generalization, leading to errors like overgeneralization, hallucination, or refusals. Developers mitigate these risks with safety guardrails, prompt engineering, retrieval-augmented generation, fine-tuning, and external tools. Despite progress, challenges remain in robustness, ambiguity, and adversarial resistance, making human oversight and careful deployment essential in high-stakes domains. Article: LLMs like GPT-5, LLAMA, and Claude have become central to how people interact with artificial intelligence. These systems power chatbots, writing assistants, code generators, and more. They are often astonishingly fluent and capable, but their behavior in unusual or unexpected circumstances, what we call edge cases, reveals both their strengths and weaknesses. Understanding how LLMs handle these situations is important for both users and developers, since edge cases can expose limitations that affect reliability, safety, and trust. This essay examines how LLMs manage edge cases, why these situations are difficult, and the various strategies used to mitigate problems. We will move through 5 main themes: the role of training data, generalization and approximation, safety mechanisms, technical approaches to handling edge cases, and the remaining challenges that continue to puzzle researchers. 1. The nature of edge cases in LLMs. In computer science, an edge case is a situation that occurs at the extreme operating limits of a system, inputs that are unusual, rare, or unexpected. For LLMs, edge cases often take the form of rare linguistic phenomena, uncommon idioms, archaic language, or niche professional jargon. Extreme numerical or logical queries, asking about very large numbers, tricky math proofs, or paradoxes. Ambiguity, prompts that can be interpreted in multiple valid ways, like legal clauses or abstract philosophical questions. Adversarial prompts, crafted to trick the model, bypass its guardrails, or expose blind spots. Out-of-distribution inputs, requests that are far removed from anything the model saw during training, such as unusual programming languages or highly specialized medical data. Edge cases are important because they test the boundaries of generalization. While LLMs excel at producing fluent and plausible text for common cases, their reliability drops at the margins. This fragility matters most in high-stakes areas like healthcare, law, or finance, where a single mishandled edge case can lead to serious consequences. 2. Training data coverage and its limits. The behavior of an LLM is determined by the data it was trained on and the algorithms used to optimize it. During training, the model is exposed to trillions of words of text, learning to predict the next token given previous ones. This training data covers a vast range of human knowledge and language use, but it is not infinite. Some patterns occur frequently and are well learned. Others appear rarely, if at all. Common patterns. For everyday conversation, popular culture, and general knowledge, LLMs perform impressively because these are heavily represented in training. Sparse patterns. For topics that only appear in niche communities, say detailed instructions for a specialized medical device or medieval Scandinavian poetry, the model may lack robust representations. Noisy data. Even when rare cases exist in the training set, they may be inconsistently labeled, ambiguous, or contradictory, leading the model to produce unreliable outputs. This explains why LLMs sometimes fail on edge cases of knowledge. If a query involves concepts that appear rarely or inconsistently in the data, the model cannot learn reliable associations. It might guess, hallucinate, or fall back on more general patterns that don't quite fit. 3. Generalization and approximation. LLMs are not databases that retrieve facts. They are statistical approximators. They generalize from patterns in training data to predict likely continuations. For most queries, this produces high-quality text, but for edge cases, generalization can misfire. Some common failure modes include overgeneralization, applying rules too broadly. For example, if most examples of math problems involve small numbers, the model may apply the same reasoning to much larger numbers, where different strategies are needed. Hallucination, generating plausible but false information. For rare or ambiguous prompts, the model might simply invent details to fill the gap. Safe defaults. Some models are tuned to respond cautiously when uncertain, preferring to hedge or refuse, rather than risk a wrong answer. This is useful for safety, but can frustrate users who want concrete responses. One useful way to think about LLM behavior is that they are probabilistic mirrors of their training data. In edge cases, where the mirror has fewer examples to reflect, the distortions become obvious. 4. Safety layers and guardrails. Because edge cases often intersect with safety risks, developers add safety layers around the base model. These include refusal mechanisms. If a query looks unsafe, inappropriate, or too far outside the model's scope, the system can decline to answer. Confidence thresholds. If the model's probability distribution over outputs is too flat, a sign of high uncertainty, it may trigger a fallback. Human-in-the-loop systems. In critical applications, like clinical decision support, humans review outputs before they are acted upon. Safety layers are particularly important because some edge cases are adversarial. They are deliberately designed to exploit weaknesses. For example, a user might phrase a harmful request in an unusual way to trick the model into answering. Strong guardrails help prevent such exploits, though the problem is ongoing. 5. Techniques for handling edge cases. Beyond safety layers, developers employ a variety of technical methods to help LLMs cope with unusual inputs. A. Prompt engineering. Carefully crafting prompts can make models more reliable in edge cases. Adding structure, think step by step. First list the assumptions, then give the answer. Often leads to better reasoning. This helps especially for math, logic puzzles, and ambiguous queries. B. Chain of thought and reasoning strategies. Some systems allow models to generate intermediate reasoning steps before producing a final answer. This reduces leaps of intuition and improves performance on tricky tasks, though it can slow response time. C. External tools. Instead of handling everything internally, LLMs can call external systems. Calculators for precise math, code execution environments for programming tasks, retrieval systems that fetch documents from trusted databases. This approach, often called tool use or retrieval augmented generation, RAG, improves reliability by grounding outputs in verifiable sources, fine-tuning, and domain adaptation. For applications in medicine, law, or other specialized domains, developers often fine-tune a general LLM on curated datasets. This increases coverage of edge cases that matter for that field. E. Few-shot and in-context learning. By including examples of edge cases directly in the prompt, users can guide the model to better performance. For example, showing it how to handle unusual formatting or rare terminology gives it a scaffold to follow. 6. Examples across domains. To make this more concrete, let's look at how edge cases show up in different contexts. Mathematics. An LLM may solve simple algebra flawlessly, but stumble on large prime factorization because it lacks algorithmic reasoning. Tools like Python execution help bridge this gap. Programming. For common languages like Python or JavaScript, LLMs are strong, but for obscure languages like COBOL, performance drops sharply, an edge case due to data scarcity. Medicine. A model might perform well on general health advice, but fail on rare diseases or unusual presentations of common illnesses. Fine-tuning and human review are crucial here. Law. Ambiguous or edge case legal language can lead to multiple plausible but conflicting interpretations. Human expertise remains essential. Language. An LLM might understand standard English idioms but fail with regional dialects, mixed language code switching, or highly archaic text. 7. Remaining challenges. Despite progress, several challenges remain in handling edge cases effectively. Out-of-distribution robustness. Models are still brittle when faced with unfamiliar contexts. Ambiguity resolution. Many edge cases don't have a single correct answer, making evaluation difficult. Adversarial robustness. Attackers continue to find new ways to exploit edge cases to bypass safeguards. Transparency. LLMs rarely communicate uncertainty clearly, making it hard for users to know when an edge case is being mishandled. Researchers are exploring methods like uncertainty estimation, calibration techniques, and explainable AI to improve trust and reliability. Conclusion: edge cases are the stress tests of large language models. They reveal the limits of training data coverage, the quirks of probabilistic generalization, and the importance of safety mechanisms. While LLMs handle many everyday situations with remarkable fluency, edge cases remain a frontier where reliability breaks down. The strategies to manage them, from prompt engineering and chain-of-thought prompting to retrieval-augmented generation and fine-tuning, represent a growing toolkit for developers. Yet human oversight, especially in high-stakes domains, remains essential. In the long run, better training methods, more robust reasoning architectures, and clearer communication of uncertainty will help LLMs navigate edge cases more gracefully. Until then, edge cases remind us that while LLMs are powerful tools, they are not infallible, and thoughtful design, careful deployment, and human judgment are key to using them responsibly.